What if the numbers we use, the ones we use to describe the world, weren't actually fixed? Not static points on a line, but fluid dynamic entities, things that changed based on context.
It's a pretty mind-bending idea when you first encounter it, isn't it?
It really is, because for so long, our understanding of reality, how we measure it, quantify it, it's all been shaped by the mathematical tools we had.
Right. We've operated under this assumption that, 5 is always 5, a dimension is fixed, time flows at this unwavering rate.
Exactly. But what if those very assumptions, the ones baked into our traditional math, were actually limiting us? What if they were stopping us from seeing the inherent irregularities, the dynamism, the interconnectedness of everything?
Preventing us from grasping the full picture, perhaps.
Yeah.
The tapestry of a living, evolving reality.
That possibility, that very intriguing possibility, brings us to today's deep dive. We're going to plunge into the insights of Philip Randolph Lilien's groundbreaking paper, Integration of Fractal Calculus with NFN Numbers. Our mission today is really to unravel these complex, but honestly completely captivating concepts. We want to uncover how these NFN numbers, these non-fixed number frameworks, aren't just enhancing fractal calculus, but maybe fundamentally revolutionizing it.
Yeah, offering a new lens, really.
A new lens to view complex systems, maybe even the fabric of reality itself. So yeah, prepare for a journey that might challenge some basic mathematical intuitions.
And it's important to stress, this work by Lilien isn't just some theoretical tweak in pure math. It feels like a foundational shift.
How so?
Well, it directly confronts the limitations we hit when we try to use conventional math on inherently irregular patterns. Things that are unpredictable, dynamic.
Like what kind of things?
Oh, everything from, say, the branching of neurons in the brain to chaotic weather systems, the fractal shapes of coastlines, or even, the adaptive behaviors in economic markets. Traditional math struggles there. So, by introducing NFNs, Lilien provides a framework that can actually mirror these realities much more closely. And the implications, well, they stretch far beyond just math. It really opens up new ways of thinking, new avenues for modeling in physics, biology, ecology.
Even consciousness, perhaps?
Potentially, yes. It's about building a mathematics for a world that's, alive and constantly changing.
Okay, so let's unpack this a bit. Before we dive headfirst into NFNs themselves, maybe we should set the stage. Let's talk about what fractal calculus already does and why it was needed in the first place.
Good idea. Because we all kind of intuitively know the world isn't made of perfect geometric shapes, right?
Right. No perfect circles or straight lines out there, not really. Look at a mountain range or a cloud or even the branching of a tree.
Or the blood vessels in our own body.
Exactly. They're all inherently irregular. They're not Euclidean. And traditional calculus, the math of smooth curves and fixed dimensions, it really struggles to describe those things accurately.
It struggles mightily, yeah. It's built for an idealized world, often a linear one. It works beautifully if you're modeling, say, a perfect parabola or a smooth wave.
But nature isn't like that.
Not usually, no. When you get into natural phenomena, things with self-similarity across scales, where details just keep appearing the closer you look, classical calculus just hits a wall.
And that's where traditional fractal calculus came in.
Precisely. It tried to bridge that gap. It moved beyond whole numbers for derivatives and integrals. So instead of a first or second order derivative implying smooth change, you might have, say, a 1.5th order derivative.
Okay.
And to quantify this roughness or complexity, it introduced concepts like scaling exponents. You see symbols like alpha, beta, or the famous Hausdorff dimension, DHX.
Right, I've heard of the Hausdorff dimension.
Yeah, these exponents try to capture the fractal dimension, that non-integer measure of how much a fractal fills space.
But even those had limitations. That's where Lilien comes in.
Exactly, and this is critical. Even these scaling exponents, as revolutionary as they were, have inherent limitations. Lilien's paper points out a few key things. First, they're local, not global.
Meaning
they describe properties at a specific point or maybe a small region, but they don't necessarily hold true across the entire system. The roughness might be different over here compared to over there.
Okay, that makes sense.
Second, they're dimensionally modulated. Their values can actually change depending on the dimension or scale you're looking at. Adds complexity.
Right.
And maybe the most crucial point, they are often non-analytic or transcendental.
Which sounds complicated. What does that mean practically?
It means these exponents can be incredibly difficult to pin down precisely with our usual fixed number system. They often defy simple algebraic formulas or exact calculation. They're just messy in a way.
So they get us closer, but still not quite there for truly dynamic systems.
Exactly. Think about trying to precisely measure the edge of a flickering flame or the turbulence in a river. These exponents were better than classical numbers, but they still operated on a kind of static principle within a dynamic reality. They struggled to capture the fluidity of the change itself.
That distinction, local versus global, and them being non-analytic?
Yeah, that clarifies the problem. It's like that analogy you sometimes hear, trying to map a constantly swirling cloud with a ruler that only has fixed markings, even fractional ones.
Right. You get an approximation, but you miss the continuous subtle changes.
Or, even if your ruler could measure tiny fractions, what if the definition of an inch itself was subtly changing based on the cloud's internal state, its energy, its coherence? You'd still be off.
That's a great extension of the analogy. It's not just about finer markings on a fixed scale. It's about the scale itself potentially being responsive.
And that inability to capture a fluid, non-fixed reality.
Yeah.
That's why we need something new, a new kind of number. That's precisely the motivation. We need a number system that can, in a sense, breathe with the system it's describing. And this brings us directly to Lilien's big contribution. NFN numbers, non-fixed number or non-finite numeric frameworks.
Okay. So not just an improvement, but a whole new paradigm.
That's how it's presented, yes. A fundamental shift. They're specifically designed to tackle those limitations we just discussed, offering a really different way to quantify and interact with dynamic reality.
So what makes them different? What are their core characteristics?
Lilien defines them carefully. First, they're built to accommodate variable scaling exponents. So unlike that fixed alpha in older fractal calculus, an NFN number can represent an exponent that is itself changing, adapting.
Okay, variable exponents, got it.
Second, they represent non-integer, scale-relative, and dynamically modulated quantities. This means they capture values that aren't just fractions, but are tied to the scale you're observing at, and they can shift dynamically during the observation.
Scale, relative, and dynamic. Okay.
Yeah. But here's the most striking part, where the deeper implications really start. NFNs are designed to express values that are contextual and coherence-dependent, not statically fixed.
Okay, hold on. Contextual and coherence dependent. That sounds really different. Contextual, I sort of get, depends on the surroundings. But coherence dependent. What does that mean in this kind of advanced math? It almost sounds like the number itself is responsive.
You've absolutely zeroed in on the core innovation there. Yes, responsive is a good way to think about it. Coherence dependence means the value of an NFN number isn't some absolute predefined thing existing separately from the system.
Okay.
Instead, its value emerges from and is deeply influenced by the underlying coherence field, the internal consistency, the order within the system it's describing.
So it's not just a label, it reflects the system's internal state.
Exactly. Think of it less like a fixed point on a number line and more like a dynamic property that arises from the web of relationships inside the system. If the system's internal order, its coherence, its resonance changes, the NFN describing some property of that system also changes correspondingly.
Wow. Okay. So that makes them perfect for fractals, where the parts and the whole are constantly interacting and influencing each other.
Perfectly suited, yes. It allows the math to genuinely mirror that dynamic, irregular nature. It lets the mathematics breathe with the system.
So is there a key takeaway sentence here, the aha moment?
Yes, and Lilien states it very clearly in the paper. Fractal calculus therefore requires a number system that can fluidly move between integer, fractional, irrational, and context-modulated values, which is exactly what NFN enables.
Fluidly move between different types of values, even context-modulated ones.
Right. Our traditional number system, even complex numbers, is fundamentally rigid. It assumes a fixed backdrop. NFNs challenge that. They offer a language for a reality where the rules themselves are dynamic, emergent, tied to the system's internal state.
That fluidity is the key, then, unlocking a new level of description for systems that just defy static measurement.
It allows for a truly adaptive, almost living mathematics.
Okay, so we have these NFNs, fluid responsive numbers. Now, how do they actually change the tools of calculus? Let's start with derivative. A derivative tells us the rate of change, right? How steep a curve is at a point, instantaneous change.
That's the classical idea.
So how does fractal calculus, especially with NFNs mixed in, rethink that fundamental concept?
Well, in traditional calculus, even in the earlier fractal versions, you use a fixed order derivative,
Yeah.
written like daf x dia, where alpha is a specific unchanging number, maybe 1 for classical change, maybe 0.5 for some fractal
Like
roughness.
single constant order.
Exactly, applied uniformly. But Lilien introduces the fractal coherence derivative in NFN form.
Okay, sounds fancy. What's the essence of it?
The formula itself looks complex. dx fx lim epsilon 0 fx plus epsilon fx epsilon.
Whoa, okay. Lots of symbols there.
Yeah, but let's focus on the implication. It still uses that limit concept, epsilon going to 0, for instantaneous change. But the huge difference is the exponent, ax. That little tilde means it's an NFN number.
Ah, so the exponent itself is fluid.
Precisely. And notice epsilon is raised to the power of that NFN number. So the very step size you're using to measure the change is also dynamically modulated by this fluid exponent.
So it's not just the order of the derivative that's non-integer, it's variable. What does that let it do?
That's the transformative part. Because AX is an NFN, it's not static. It varies dynamically. And crucially, it reflects coherent scaling relationships, not just static geometric properties.
Okay, unpack that. Coherent scaling relationship.
It means the rate of change you calculate isn't just about the shape of the curve anymore. It adapts based on the internal coherence of the system, its level of organization, its resonance, maybe even how it's interacting with an observer.
So the steepness depends on the system's internal state, not just its geometry.
Exactly. It allows for continuously adjusting derivative orders across hyperfractal domains. The very nature of how change happens can itself change, responding to the system's underlying logic or state.
That's quite a shift. Let me try an analogy. Calculating a car's speed. Normally, miles per hour is fixed, but here it's like the unit miles per hour itself could change dynamically based on road conditions, engine health, driver focus.
That's a really good way to think about it, yeah. The mathematical ruler for measuring speed isn't just more precise, it's adapting in real time to the context.
And this allows movement across hyperfractal domains. What does that mean? Different layers of reality?
Conceptually, yes. Think of different scales or states within a complex system. Maybe the molecular level, the cellular level, the organ level in biology. Each could be a hyperfractal domain. This NFN calculus allows for analysis between these layers. It's not a flat calculation. It's multi-dimensional adaptive measurement reflecting the true complexity. It means we can model things where the rules of change aren't fixed constants, but emerge from the system's current evolving state and its coherence.
A math that acknowledges how interwoven scale and context really are. Okay, so derivatives get this dynamic, coherent, sensitive upgrade. What about the flip side integration? Summing things up to find a total, like, area under a curve or volume. Traditional integration uses fixed little bits, right?
Right, summing up tiny rectangles of fixed width, essentially. Even standard fractal integrals like arip fx xx1 dx use a fixed fractal dimension alpha. It accounts for irregularity better than classical integrals, but the measure, the unit of summing, is still static.
So it assumes the little bits you're adding up are all the same kind of bit?
Exactly. Lilien extends this with the NFN extended form, fsx1dx. Notice the domain A is now a hyperfractal domain, suggesting a complex layered space.
And there it is again, AX, the NFN exponent. So that's the game changer for integration too. How does it affect the measure, what Lilien calls DNFNX?
It completely transforms the measure. The NFN fractal measure, DNFNX, isn't static. It dynamically adapts. It responds to multiple factors.
It does.
The source highlights the local coherence field strength, CX, the system's internal order. Also, observer impact, acknowledging measurement, can affect the system. And even dimensional collapse or emergence events, where the system's basic structure might suddenly shift.
Wow. Observer impact and dimensional collapse. That's deep.
It is. It means when you're summing up over an irregular changing domain, the very units you're accumulating aren't fixed. They adapt moment by moment based on the system's coherence, how it's being watched, even shifts in its dimensionality.
So each tiny piece carries information about the system's internal state.
That's the idea behind hyperfractal measures where every infinitesimal carries an embedded coherence logic. Each tiny slice isn't just geometry, it holds information about the internal order and relationships at that point.
Like the measuring ruler has built-in feedback.
Kind of, yeah. It's responding to the internal state of what's being measured, not just its external shape. This allows the integral to detect resonance thresholds, instability points. It's a huge leap. It moves from passive measurement to active dynamic quantification.
So what does this mean overall? Our measurement becomes an interaction. The system's internal state influences how it's measured.
Precisely. It's radically different. It moves beyond static observers and fixed metrics to an interactive, responsive framework, like trying to measure the total emotion in a conversation. You can't just count words. The measure has to adapt to tone, context, relationships.
So NFN integration allows for a much more accurate picture of reality for systems in constant flux, systems governed by coherence.
Exactly. It could be revolutionary for things like adaptive materials or understanding information content in quantum systems where static models just fall short.
Okay, NFNs are reshaping space and measurement, but what about time? We usually think of time as, linear. Tick-tock, 1 second after another, same pace everywhere.
The single river flowing uniformly, yeah. That's the classical picture.
But Lilien's work challenges that too, suggests time might not be so fixed.
It pushes our understanding right to the edge here. Lilien introduces the concept of multiple temporal axes, T1, T2, T5.
5 time axes?
Potentially, yes. Suggesting not just one timeline, but maybe multiple intertwined temporal dimensions or layers operating at once. And crucially, these can be indexed using NFN exponents for each axis, written as TNN.
So each time axis has its own dynamic NFN rate.
Exactly. It immediately implies a multidimensional dynamic view of time, where each axis's flow or character is modulated by an NFN responding to local conditions, a huge departure from a single universal clock.
How does that play out in the math? Is there a time derivative?
Yes, and it integrates this NFN index dynamism. The formula looks like NN, CNTN index, epsilon, CNTN. Okay, again, complex formula, but what's the core idea? We're differentiating over a time axis whose very texture or rate of progression is dynamic. It's influenced by both its NFN exponent and its local coherence field, CNTN, at that temporal point. Even the epsilon step size is modulated by this dynamic combination.
So the fabric of time is woven by the system's coherence.
That's the implication, yes.
Mind blown. Okay, so if each on is an NFN dynamically changing, what does that mean for time in, say, a biological system or a quantum process?
It means each NFN exponent on becomes a dynamic resonant scalar that indexes the dimensional coherent state of time itself.
A dynamic resonant scalar indexing the coherent state of time itself.
Yeah. So the flow or structure of time locally isn't uniform or predetermined. It adapts based on its own internal coherence, its resonance with the system, maybe even observer interaction.
So back to the river analogy, time isn't one river.
It's more like a complex, multi-branched river system. The current in each branch can speed up, slow down, form eddies, maybe even stop flowing for a bit, all depending on the dynamic interactions and coherence within that part of the system.
So time might flow differently in a highly coherent biological process versus a chaotic quantum event.
That's the kind of nuanced understanding this framework allows for. It suggests time is part of the adaptive landscape, not just a static backdrop.
Like how our brains process information or biological clocks.
Yeah.
Could this model how time perception or biological time warps locally based on the system state?
It potentially could, yes. It implies time isn't just something we move through, but a dynamic variable that can be shaped by the systems existing within it.
Okay. NFNs redefine derivatives, integrals, even time, making them fluid and responsive. So Lilien brings this all together in what he calls the NFN Integrated Universal Cohesion Equation. UCE sounds big.
It is aiming for a big synthesis, yeah. A comprehensive description of dynamic systems. The UCE formula is written as RDX.
All right, let's break that down. R.
R is a coherence operator. It acts on the NFN enhanced fractal derivative that follows it.
And inside that derivative, dx, cx, we have our dynamic NFN exponent, x.
Right, which is fluid and context dependent, but it's also modulated by cx, the local coherence field. So the rate of change itself is directly impacted by the system's internal order or harmony.
Okay. And x is the system state.
It's the wave function or coherent state.
And on the right side, x?
X is the coherence eigenvalue. And crucially, this is also an NFN number.
Also an NFN, so it's not a fixed constant.
No, it's a dynamic value reflecting the overall coherent state of the entire system. So the equation basically says, a coherence operator acting on the NFN modulated rate of change to the system's coherent state equals a dynamic coherence eigenvalue times that state.
That is a lot part, but incredibly powerful sounding. Connecting it to the bigger picture, what does this UCE let us capture that traditional math just can't?
It offers a truly holistic framework. It can describe systems where scale, time, and coherence aren't static, but are in constant dynamic interplay. The source highlights it captures variable scaling.
Meaning the fractal dimension itself changes?
Yes, dynamically, based on the system's coherence. Think of a storm system whose fractal patterns shift as it organizes or dissipates.
Okay. What else?
It models fractal space-time interactions, how the geometry of space and the flow of time are linked and influence each other in complex, dynamic ways, modulated by their fractal nature and coherence, maybe going beyond even what general relativity describes in certain contexts.
Wow.
And perhaps most critically, the UCE captures dynamic emergence or collapse of coherence, the spontaneous formation of order from chaos, or its sudden breakdown.
So it's a mathematics for a living, evolving reality, where properties emerge and dissolve based on coherence.
Exactly. It's an adaptive mathematical language where the rules aren't just discovered but are, in a way, being written by the system itself as it evolves.
That brings up a key point then. Coherence here isn't just a nice idea like things hanging together. It's a quantifiable dynamic field.
Absolutely. CX, the coherence field, isn't just descriptive. It's operational, quantifiable. It exerts a direct influence on the math.
How?
It directly modulates those NFN exponents that define rates of change in measures. Its intensity, its dynamics, determine how scaling happens, how time flows locally, how the system evolves. Think about coherent laser versus diffuse light, or an organized ant colony versus scattered ants.
The coherence isn't just an outcome, it dictates behavior.
Precisely. The UCE provides the mathematical machinery to understand how order arises, shifts, or falls apart, not due to external forces necessarily, but as intrinsic properties of the system's own evolving coherence. So let's just circle back and really emphasize this core idea. NFN numbers, especially that dynamic exponent ODEX, aren't just arbitrary variables. They act as coherence-based scalars.
Meaning their value comes from the coherence.
Yes, their specific value is intrinsically linked to, derived from, the coherence field intensity CX. The level of internal order, or how that order changes, directly dictates the numerical value of these NFNs. It gives them this built-in sensitivity, a feedback loop, to the system's organization.
Right.
And we really need to re-emphasize the implications of that coherence-modulated NFN derivative, FX. It's revolutionary because it allows scaling orders to vary locally. One part of a system might have one fractal dimension, another part a different one, all dynamically determined.
Okay.
Plus, these orders respond to coherence resonance. They change in sync with the system's internal harmonics or patterns of order.
Yeah.
And crucially, this allows the system to potentially traverse between dimensional layers of reality.
Traverse between dimensional layers. That sounds like science fiction almost.
It pushes boundaries for sure.
Yes.
It's not just about different geometric scales, but potentially shifting across fundamental states of organization or existence within the system.
Okay, this goes way beyond simple geometry, even beyond standard physics. It implies this responsiveness is built into the math, describing systems that are adaptive, self-organizing, but traversing dimensional layers. What could that actually look like in a real-world scenario? Conceptually, like emergence, phase transitions.
That's a great way to frame it, and conceptually, yes, you're on the right track.
Yeah.
While the paper doesn't give specific real-world examples of traversing layers, it could relate to things like emergent properties.
Like consciousness from neurons.
Exactly. Individual neurons are one layer. Consciousness emerges as a qualitatively different layer. This NFN framework might provide the math to model how that happens, how the coherence of the parts leads to that shift in the whole.
Or phase transitions, water to ice.
Another excellent conceptual fit. The substance shifts from one state, one dimensional layer of organization, to another with totally new properties. Lilien's calculus, by adapting its descriptive power to the changing coherence and dimensionality, could potentially model the dynamics of that transition itself, not just the before and after states.
So it's about modeling the process of becoming something new.
Yes, mathematically navigating and quantifying these profound transformations where the system's rules fundamentally change as its coherence shifts. And this framework doesn't just describe, it also offers powerful insights into stability and instability. Lilien talks about NFN-driven resonance, collapse, and stabilization. This is huge for prediction.
Predicting when systems might break down or find balance.
Exactly. He identifies destabilization points. These happen when that combined term, the NFN exponent times the coherence field, tends towards either 0 or infinity.
Okay, 0 or infinity, what happens then?
When it heads towards 0, it indicates coherence collapses or resonance annihilation. This is where the system loses its internal order, its connections break down, it dissolves into chaos.
Can we imagine that, like a bridge vibrating itself apart?
Hmm.
Or maybe an ecosystem losing its balance suddenly.
Those are perfect conceptual examples, yes. Or think of a market crash where the interconnectedness fails. That's a coherence collapse.
Okay, and when it goes towards infinity.
That signals critical amplifications or resonance inflation. Uncontrolled growth, runaway feedback loops, extreme instability that could destroy the system through overexpansion.
Like the bridge resonance example again, but amplifying uncontrollably. Or maybe a tumor growing out of control in biology.
Exactly. Or a rumor spreading virally, causing self-reinforcing panic. That's resonance inflation growth mechanisms become destabilizing.
So, points of breakdown or runaway instability, what about stability?
Stabilization points occur when that same product, x, cx, equals a constant. This isn't static rigidity, though. It's a dynamic equilibrium across the hyperfractal geometry.
Dynamic equilibrium, meaning?
The system maintains order through continuous adaptive adjustment. Balance achieved through constant motion and recalibration, like a healthy ecosystem maintaining resilience despite fluctuations.
So NFN calculus could pinpoint both crisis points and states of dynamic balance.
That's the power. It offers a mathematical tool to identify these critical thresholds in highly complex changing systems. It moves us toward prediction and potentially management.
That really is game-changing, not just describing complexity, but potentially predicting its critical turns across so many fields: engineering, climate, economics.
It's about understanding the thresholds of chaos and order.
Okay, I think we can agree these concepts are profound, but also incredibly abstract. It's hard to really visualize coherence fields modulating NFN exponents that change integration measures across hyperfractal domains.
It definitely stretches the imagination, yeah.
And Lilien recognized this challenge. He proposed a visual, a scroll-style visual.
Yes, exactly. A way to try and make these dynamic interactions more tangible, more intuitive. The scroll-style visual. Fractal derivatives from NFN modulated scaling curves.
Okay, paint us a picture. What would the scroll look like?
Imagine a continuous scroll unfurling like an ancient map, but dynamic. It's not just a static graph. It's a complex, evolving landscape of functions.
What are the key features?
Okay, first, along the bottom, an x-axis. That's your input domain x, the variable you're tracking.
Standard enough.
Then across this domain, you see multiple curves. Not just one, but various coherent scaled functions, fx. Each curve is shaped by its own dynamic NFN exponent, fx. So you see this family of curves morphing and interacting as you move along the scroll.
So the curves themselves are alive, changing shape.
In a sense, yes. And overlaid on them are dynamic tangent arrows. These show the slope, the rate of change. You'd see arrows for classical change, maybe fixed fractional change, 0.5, but crucially, the dynamic NFN varying slope driven by apex.
So the tangent arrows themselves would be changing direction and length along the curve.
Exactly, visually demonstrating how the rate of change is constantly influenced by both the fluid NFN exponent and the local coherence.
That's clever. What else?
There'd be an overlay. The local coherence field strength is color gradient. So CX gets visualized. High coherence areas might glow brightly. Low coherence areas might dim or change color. You literally see coherence shaping the landscape.
Wow, okay, like a heat map of order.
Kind of, yeah. And a side legend would map the product IC to local resonance modulation, telling you if the system is stable, inflating, or collapsing based on the colors and arrows.
And a spiral motif.
Yeah, a spiral motif showing how curves fold into higher resonance orders. Maybe visualizing how complexity emerges or how the system jumps between those dimensional layers we talked about.
That is actually a brilliant visualization. It makes the abstract concrete. It shows the dynamism, the layers, how coherence literally shapes the math, and thus the system. It's not just numbers, it's a living map.
Exactly, a map that breathes with the territory it describes. It has bridged that gap between the complex equations and intuitive understanding. Hashtag ouchtag outro.
What an absolutely incredible journey today, diving into Philip Randolph Lilien's work. We started by questioning something as basic as numbers, imagining them as fluid, responsive. Then we plunged into NFN numbers, saw how they could redefine derivatives, integrals, making them dynamic, context-dependent.
Reshaping the very tools of calculus.
We even stretched our minds to consider dynamic time axes, a multidimensional fluid time. And it all came together in that universal cohesion equation, the UCE.
A framework trying to capture that interplay of variable scaling, fractal space-time, and dynamic coherence.
It's really quite something.
Indeed. And as we often say, knowledge is most valuable when understood and applied. This isn't just abstract math theory. Lilien's work here, it really lays down a potential blueprint for new ways of understanding and modeling these incredibly complex adaptive systems that define our world.
From physics and biology.
To economics, ecology, maybe even consciousness. It offers a language, potentially, to describe things that were just beyond our grasp with fixed mathematical tools. It's about shifting from a static view to one embracing dynamism and interconnection.
So what does this all mean for you listening? Well, it means our understanding of reality, the tools we use, they're far from finished. This deep dive really challenges those fundamental assumptions about reality being fixed. It pushes us to think about a world where even numbers are dynamic.
And if the very numbers describing reality are dynamic, context-dependent, and if they're linked to this underlying coherence field, dictating how things evolve.
Well, what does that imply about reality itself? Is it more stable or more malleable than we think? Could NFN numbers eventually help us not just understand, but maybe predict or even interact with complex phenomena, from weather patterns to the emergence of consciousness?
Could we do it in ways we never thought possible, just by tuning into their underlying coherence?
It leaves us with that really tantalizing thought. Maybe our universe is far more responsive, far more alive than our current mathematics even allows us to perceive, something to definitely ponder.